Okay, so the last online lecture that I want to make sure that you guys know about is the concept of regression and correlation. So this I never know where to stick this, so I always do it at the end of experimental design, but it's actually not an experimental design, it's a different method of analysis. So we've talked primarily about analysis of variance or ANOVA, and so that is one way that we can analyze data. We also talked very briefly about a student's t-test or a paired t-test. That's also a way that we can determine if two means for a sample group actually differ and if our treatments had any effect. But one other way that we can look at the relationship between a set of traits is through a regression and a correlation analysis. So just to give you a little bit of background about why we use these, regression and correlation are really used to identify relationships, and we can use those relationships to actually make predictions. These are two staples of data analysis that we tend to run anytime that we're looking for relationships between traits. So some things that these two analyses can kind of answer for us are the questions: can I predict how many units I'll sell if I spend this many dollars in advertising? If does drinking more Diet Cola really relate to more weight gain? And then, do children's backpacks seem to get heavier with each year of school, or is it just me? So those are questions that relate two different traits to one another. So let's talk specifically about regression very quickly. So regression comes in many forms. The one that we're going to talk about today is linear regression. And linear regression identifies a relationship between two or more variables, and then we'll calculate a model that tries to describe that relationship. So some common examples in animal science of regression relationships include the scrotal circumference of a sire and compared to the age at puberty of his daughter. So two very different traits. And then on the agronomy side, if we tried to look at the relationship between a concentration of fertilizer application on the yield in alfalfa, a regression analysis can actually help us answer those questions. So regression analyses actually try to fit a line. And in fitting that regression line to a set of data, we have to assume that the data actually follow a linear model. So keep in mind that this relationship here is what we've been studying all along. As we've expanded our experimental design, we've looked at more in-depth analysis variance, we've accounted for more sources of variation associated with our response variables. So in this model over here in regression, we are actually looking at a true slope line. So where our estimated response variable is equal to the mean, and then we also identify the true intercept. So the intercept is going to be a part of this equation in addition to the estimate of the true slope. So when we run a regression analysis, which you can do in lots of different software packages online or even in Excel, you're going to get your data set needs to look something like this, to where you've got trait 1 for an individual experimental unit and trait 2 for that same individual experimental unit. And those two pieces of information need to be within the row where one row is for an experimental unit. So in this example, we've got a live weight, and we're comparing that to a dressed weight, or a slaughter weight. And so we treat the live weight as our independent variable, and we treat the dressed weight as our dependent variable. So in the context of independent and dependent variables, the live weight would be like our treatment, and the dressed weight would be like our response variable. So the next step in a regression analysis is that we plot our two variables against one another in a scatter plot. So down in this figure, we would plot our live weight against the dressed weight for that individual animal. And once we get the scatter plot established, we can then ask ourselves a question of, does our observations appear to fall in a linear pattern? And if the answer is yes, then we can fit a line to that pattern and develop a regression equation, where the regression equation generated by the software, and this is where we actually have our estimated y value, or our estimated response variable, and then we've got our slope and our true intercept here. And so our regression analysis will also give us an R-squared value, or a regression value, and that regression value is going to lie between 0 and 1. And the higher it is, so the closer to 1 it is, the more confidence we can actually put in that regression. So this is 0.9, so that we are pretty confident that the live weight is going to dictate the dressed rate. And so we can actually, if we have a live weight, we can actually plug that in here as x, multiply that live weight times 0.6163 and add 0.086 to get a prediction of the dressed weight. So this is an example of something that we do all the time. All the equations that we come up with for predicting or, ribeye area or back fat percentage or any of those type of things are all based on regression analyses. So when we run a regression analysis in a software program, we're going to get 2 tables worth of information. This is the first one. So the statistics associated with the regression analysis are going to give us 5 different numbers. So our multiple R number indicates the absolute value of correlation between the dependent variable and the predictor variables. Our R-squared value that we looked at, I'm going to flip back, don't freak out, this is our R-squared value. That R-squared value is coming from this position on that statistics chart, and that is the coefficient of determination. So that R-square value is going to tell us the proportion of the variability in the dependent variable that is accounted for by the independent variable of the model. So again, because it's 0.9, it's very high, we can actually account for a lot of the variation using live weight when predicting dressing percentage or dressed weight. And then the third bar, or the fourth piece of information in the statistics model, is the standard error. And so the standard error is going to measure the size of the typical deviation of an observed value from the regression line. So let me flip back for just a second. So we're actually looking at the number of, or the amount of space in between these individual points compared to this regression line. All right, the second piece of information, or the second table that's going to be generated as part of the regression analysis, is this coefficient table. So on the left-hand side, we've got our intercept variable, and then we've got our predictor variable, so our live weight. And so the coefficients here we're going to use to actually build our regression equation. So in our regression equation, if we're trying to determine or predict dressing percentage, we're going to take our intercept value of 0.86, then we're going to add it to the live weight coefficient, which is 0.6162, and multiply that times x. And so this tells us that for every 1 unit increase, or 100-pound increase in live weight, we can expect a corresponding 0.616 unit increase in dressed weight. And so that 0.616 unit increase translates to 61.6 pounds of dressed weight. So for every 100 pounds of live weight, we're going to get back 61.6 pounds of dressed weight. And for those of you beef cattle people in the room, that ironically is the dressing percentage for cattle on a pretty consistent basis. All right, so our regression analysis is then going to be ran through analysis of variance as well. So we're just building on the complexity of these regression analyses, and we're going to do so with an analysis of variance. So our sources of variation are going to be associated with the regression model, the residual value. So we're going to have degrees of freedom as well as the sums of squares for each of those. And when we calculate it out, we get our F statistic and then our p-value. And as you can see in this example, our null hypothesis relates to the relationship of the linear values. So because the p-value is less than 0.05 in this example, we can reject the null hypothesis that that states that there's no linear relationship between live weight and addressed weight. We have clearly shown that there is a relationship, and it's a very strong relationship between a live weight and addressed weight. So we would fail to reject our alternative hypothesis in this case, and we would reject our null hypothesis. So in order to have a valid regression model, we have to check we make certain assumptions of our regression model. So those important assumptions are fourfold. So first of all, we assume that the straight line model is actually correct. The second assumption is that the error term is normally distributed with the mean of 0. The third assumption is that the error values are consistent. And the fourth assumption is that the error values are actually independent of one another. So they're not dependent or caused by individual experimental units. So in order to check our assumption, first and foremost, we check linearity because that's our first assumption. So what we would do is we would plot the residuals on a scatter plot to try to assess if a linear line is actually could actually be created here. So when we say we plot the residuals, that means that for every experimental unit, we take the response variable and subtract it from the mean of the group. And that value is the one that gets plotted. So that's why these residual values all hover around 0. So the second assumption that we have to check is where we test for constant variance of the residuals. So to do this, we're going to plot the residuals of the regression analysis against the predicted values. So this could also be used to test for the independence of the residuals as well. As long as you don't have data points that are very weird looking or in very different spots, then you are okay. So in this case, we're okay because they're all kind of congregated around this region. However, if we had extremes, like we had one guy down here or one guy clear over here, that is when we would backtrack and relook at our model. And so when we look for normal distribution, what we would do is we would use a normal probability plot, and that's what this actually looks like. So we would then, this is produced when you run a regression analysis, but what it is it splits all of your response variables into percentiles, so 0% clear up to 100%. And then it plots that percentile based on the response variable or the dressed weight. So if the dressed weight is very low and you have very few of those that are actually reporting as a dressed weight, and you have quite a few of them that are up in this higher percentile, we can assume that our data follows normal probability.